Hello everyone. Welcome to our webinar on modeling cables and transmission lines with PSCAD EMTDC. We will begin momentarily. I'm pleased to announce our presenter, Dr. Jiwanta De Silva.
Hello everyone. I'm Jiwanta De Silva, and our simulation expert Lalin Kotlaval is also with us. So in this webinar, I would like to cover several topics, including transmission line models in PSCAD, basic modeling of transmission lines and cables, and I would like to also discuss features such as transposition, mutual coupling, DC correction, and etc. And all these are demonstrated with application examples. This webinar is mainly focused on cable and transmission line modeling. So transmission line and cable models are highly nonlinear because of the frequency dependency of the conductors and the ground plane. There are two methods of representing transmission lines in PSCAD EMTDC. One is called phi section, the other one is based on the distributed parameter method. So phi section is the simplest way of modeling a transmission line, consisting of lumped passive elements, and usually phi sections are used to model short transmission lines. There are three distributed parameter models: Bergeron, frequency dependent mode model, frequency dependent phase model. So in the next few slides, I would like to discuss these three one by one in detail. First one, Bergeron model. It's a single frequency model. So all parameters are derived at user specified frequency. The inductance and capacitance parameters are modeled in a distributed manner. We can think about it as an equivalent circuit having infinite number of phi sections. However, the resistance is lumped. It's not a distributed element. So in practice, Bergeron model is used where the specified frequency is most important in your study, and also to model transmission lines few buses away from the disturbance. So there are two frequency dependent transmission line models, mode model and the phase model. The frequency dependent mode model is based on model transformation, and there are limitations and no longer used in practical simulations. Frequency dependent phase model is the most advanced accurate cable model developed in the literature, and it accurately represents the frequency dependency as well as the distributed nature of transmission line parameters from low frequency to 1 MHz. So it's accurate for high frequency dependent configurations, including vertically asymmetrical line geometry and also underground cables. So this is a widely used in simulation studies for transient analysis. Sometimes we call this universal line model because you can model overhead lines as well as underground cables or combination of these two. So in the frequency dependent phase model is directly formulated in the phase domain to avoid problems with the model transformation matrices. So here, this table I got from the CGRE working group C4502, and this table suggests the minimum recommended cable model for different studies. For example, for cable energization, the minimum recommended model is the Bergeron model. However, frequency dependent model is used as it's a transient study. So cable segments are not important in this study. Now I'm going to show you a PSCAD simulation results. The objective of this simulation is to compare different models, transmission line models, Bergeron model, phase model, and the equivalent 5 model. So these three circuits are identical except that the transmission line is modeled in a 3 different way. So I'm applying a fault at the end of the transmission line. It's a 3-phase to ground fault, and the fault is applied at 0.51 second. I'm measuring the voltage at the terminals of each line. So if I compare the phase model with the Bergeron model, at steady state they are almost identical because the energization is done at 60 Hz and the Bergeron model is tuned to 60 Hz. So it will give a almost identical results with the phase model. However, if you apply a transient, you can see the deviation of the Bergeron model from the more accurate phase model. The Bergeron model is accurate at one frequency only. This is again a comparison of phase model with the phi model, equivalent phi model, and again you can see the differences in the transient behavior. Next, I'm going to briefly describe how to model a transmission line in PSCAD from the very beginning. Let's start a new case. I hope you're familiar with the PSCAD environment. Now, to add a transmission line, the easiest way is to click on the canvas and select component wizard. Now I select transmission line, and this is the name of the transmission line. So if you click and select edit parameters, T line 1 is the segment name. Each transmission line should have a unique name. Steady state frequency is 60 Hz. If you use the phase model, there is no important unless for display RSP values. But for Bergeron model, this is the frequency at which the transmission line parameters are calculated. So segment length is 100 km, length of the transmission line, and the number of conductors is 3. And the line termination style is local connection. We call it direct connection because you can connect the 3-phase circuit directly to this terminals of the transmission line. So you can select remote ends as well. This is another convenient way. If you model in this way, you have to add T-line interface to connect to the external circuit. So you have to make sure that the name of the transmission line and the name of the interface both are same. So you can use any of the methods, whatever convenient to you. So next, let's click on the transmission line. Now we are in the definition page of the transmission line model. So we can see the definition canvas. We don't need to worry about this one. So the default model is the frequency dependent phase model. You can add any model desired. Click on the canvas and select transmission line model, master library, virtual model if you want to add a virtual model. Now I'm going to add the transmission line tower. So you can right click and select add tower construction, master library. And this is a 3-conductor tower. If you go into the master library and the transmission lines, you can see the different towers. So if your tower is different from these models, inbuilt models, you can use universal tower model, where you can define your custom transmission line model. For simplicity, I use a 3-conductor tower, and this is the ground plane where you can define your ground resistivity. So next, what we are interested about is the sequence RXB values of this transmission line. What are the positive sequence and zero sequence values? One way is to right click on the canvas and select solve constants. So now you can see several windows here. Select the output one. From there you can find the load flow RXB formatted data based on 230 kV and 100 MVA. You can change these parameters as you wish. And here are the positive sequence and zero sequence RXB parameters based on reactance and acceptance parameters for the transmission line and also the surge impedance. We will discuss about the log line corrected later. But at the end of this page, you can see the minimum time delay and recommended time step. For any simulation, you have to select a suitable time step. So there are two considerations. One is the highest frequency of interest. For example, if you wanted to study a high frequency transient, you may have to reduce the solution time step so that you can see the transient behavior accurately. The other limitation is the shortest transmission line in your PSCAD case. Let's assume that this is my shortest transmission line. So the time delay for this transmission line is 0.0667. So there is a time delay always present when you model a transmission line using traveling wave models. So the recommended time step should be always less than the minimum time delay for this line. In this case, the recommended time step you can select as 1/10 of this one. However, I have seen even you can use 1/5 or half of the minimum time delay. But if you have lower time step, you have accurate simulation. Next, I'm going to discuss about modeling cables. Again, select component wizard and the cable. So for cables, only remote connection is available. So the parameters are same. You have to define a state frequency and segment length. And now I'm going to add 3 cables. So this is a 3 cable system in flat formulation. Let's assume that each cable has a inner conductor, main insulation, sheath, and outer insulation. So in this case, we have to change the layer configuration. C1, I1, C2, I2. This is the conductor, insulation, sheath, insulator, outer insulation. So each cable should have a unique cable number, and you can place the cable above ground or below ground by defining underground or aerial cable. In this case, it's underground, and the horizontal translation 0, and the depth below the ground surface is 1. We will talk about these things, ideal cross-bonding and mathematical conductor elimination, later. So you can enter the conductor data, the resistivity values, and also for the insulation, you can enter the durability permittivity based on the insulation property. Also, you can define semiconducting layers. All you have to enter is the semiconducting layer thickness, if there are. Similarly, you can define other conducting and insulating layers. So the cable numbers 2 is 1 meter away from cable number 1, and the third cable is 2 meters away from the first cable. So if you solve the transmission line, similarly you can see the sequence data and other information. One other thing I would like to know is, like, let's say I made a mistake. So the horizontal translation from the center I set to 0. That means I have overlapping cables, cable 1 and 2. So if I solve this one, you can't see any output. But if you go into the log window, you can clearly see the error message. From the log window, you can obtain information about warnings, errors. Next, I'm going to add the cable interface. Here I have to define the number of coaxial cables. So there are 3 coaxial cables. Then I have to define the effective number of effective conductors in the cable. So each cable has a conductor sheath configuration. Make sure that cable name, cable interface name should be same as the cable name, model name. So this is how we model a cable. So you have seen load line corrected RXB values. You may wonder what are these. Actually, transmission line parameters are calculated initially as per unit length parameters, for example resistance in ohms per meter. But what we are interested is the total RXB values for the entire transmission line. Total RXB values for the entire line do not simply equal to the per unit length RXB values multiplied by the length of the line because of the distributed nature of line parameters. However, there is a mathematical way to calculate the long line corrected data representing effective RXB values for the entire line. So there is a question for this one. There can be non-physical values in the RXB data. Resistance can be negative, reactance can be negative, because theoretically it's not always possible to find the meaningful RXB values for the entire distributed transmission line. So there can be non-physical values. So I'm discussing about the features of the transmission line and cable models one by one. One such feature we called conductor transversion. In reality, transmission lines are transposed at regular intervals. So there are two ways to model transversion: actual transversion and ideal transversion. In the actual transversion, each small line segment is modeled separately and transposed manually. Since each segment is small, you have to select a very small time step. This kind of modeling may be important in certain studies, including lightning and phase unbalance studies. So ideal transversion is an alternative way to the actual transversion. So in that case, a single transmission line model is used for the entire line, so that you can use a large time step. And there are various options. You can enable or disable the ideal transversion. However, if you have multiple circuits, the third option is meaningful, as it identifies each group separately and transforms. And this also generates sequence RXB data in the output page. So this is applicable to transmission lines with many transport segments. Now in this example, I'm going to demonstrate the effect of the transversion, ideal transversion. This is a double circuit line. One circuit is energized by a power voltage source, and the other one is not energized. I want to observe the induced voltage in the second circuit with and without transversion. Initially, let's disable the transversion. You can clearly see unbalanced voltages. Now I'm going to enable the transversion. The induced voltage on the second circuit is almost zero. It is because if you transpose this, so this circuit is transposed, and if you think about the induced voltage in conductor 6, it is the summation of induced voltage from conductor 3, 2 and 1. So since these are transpose, the distance to the conductor 6 is same. So the induced voltage just have same magnitude but 120 degrees apart, and they will cancel each other. So we can see 0 voltage here. The other circuit, the voltages are well balanced. So another feature in PSCAD is the conductor elimination and bundling. So earth wires are usually connected to the ground at regular intervals. And also, if you think about a short underground AC cables, the sheets are usually connected to the ground. In both cases, we can assume that the voltage of the earth wire or the sheet is almost 0. So with that assumption, is it possible to mathematically eliminate those conductors? It's very important to remember that mathematical elimination does not mean that the earth wire or sheet is neglected. Instead, the effect of earth wire is approximately considered. For example, losses. When you enable conductor elimination, the transmission line or cable interface should be changed accordingly. So this is applicable to earth wires and also conducting layers of underground cables, and also similar method is used for conductor bundling. Next, I would like to discuss about the cross bonding of underground AC cables. The cross bonding is used to minimize the sheet losses due to the circulating currents of AC cables. Like transposition, in cross bonding there are two ways to do that. Actual cross bonding, in here we model every details of the cross bonded system. So each minor segment is separately modeled. Alternatively, in ideal cross bonding, we can represent the cross bonded AC cable with many segments. This is of course approximate method. A single ideally cross bonded model for the entire line. So in cross bonding, sheet is ideally transposed and eliminated. So since its sheet is eliminated, the cable interface should be changed accordingly. If I take an example, now I'm going to enable the ideal cross bonding. There should be a unique cross bonding group number for each cross bonding group. So now we enable the ideal cross bonding. If you go to the interface, now you have to change the external electrical connection for each cable. Now since sheet is eliminated, to the external circuit only conductor exists. So this is how the interface. So in this PSCAD example, I would like to compare three scenarios: actual cross bonding, ideal cross bonding, and also no cross bonding. So in the actual cross bonding, we model the cross bonded system in detail, transposing at each minor section and The sheet is connected to the ground at each major section. In the ideal cross bonding, we approximate the actual cross bonded system with a single cable model. And for comparison, I compare it with the no cross bonding case. So I'm applying a fault at the terminal similarly, and I want to observe the receiving and voltages. So as you can see, ideal cross-bonded results are in somewhat close match with the actual cross-bonded system. Theoretically, if you have large number of cross-bonding segments, ideal cross-bonded should match with the actual cross-bonded system. But if you compare the actual cross-bonded system with the non-cross-bonded case, in transient simulation, there is a significant difference. For certain studies, modeling of cross-bonding is important. Now I would like to discuss about the cable models in PSCAD in detail. There are two types of cables. One is coaxial cable, the other one is the pipe type cable. So coaxial cables are used for modeling of land cables. We have discussed all these things. Data is required for each layer, dimensions, and the material properties. There is an alternative user-friendly cable data entry method. In this method, you can easily model a cable using manufacturer cable data sheet. So this is the user-friendly cable model, this coaxial cable model. From this, you can directly model 3 cables in different configurations, flat configuration or triple configuration. And you can enable or disable the ideal transposition and the cross bonding. All you have to define is the depth and the distance between conductors. Cable dimensions in the single page. And you can enter the material properties. So the conductor property can be directly entered as a DC resistance or resistivity, or there are resistivities of typical materials. You can select any of these. Insulation property can be given as capacitance or as a relative permittivity value based on the material of the insulation. Similarly, you can fill the other ones. And we have an important thing. This is called temperature dependency. Resistances are temperature dependent, and manufacturer data sheet usually use data at 20 degrees. But in reality, the conductor temperature can be much higher than 20 degrees. So if I assume 90 degrees, the AC resistance will change. To correct that one, we have to enable the temperature dependency. Other cable model is the pipe type cable model in PSCAD. So this is typically used for model the submarine cables. So there is a common pipe conductor encircling the coaxial cables. So if I slightly demonstrate the construction of the pipe type cable, we have to go to the component insert cable and select cable constraint pipe type cable. Let's assume this is a subsea cable and we have to change the resistivity to mimic the resistance of the seawater, and it is 20 meters below from the seawater. So in this pipe, by default there are 3 cables inside the pipe. So now I'm going to create the interface for this one. So there are 3 cables inside the pipe, and also each cable has a conductor sheet configuration, and you have to enable pipe conductor. So we have connection to the external connection to the pipe. So now we would like to discuss about the practical cable modeling. Usually users are given cable data sheet. This is a cross section of a typical land cable, and we can see several layers. Now the problem is, how do we fit that cable into PSCAD cable configuration? In PSCAD we have conductor insulation configuration. So the first step is to identify what are the conducting layers, insulating layers, and also semiconducting layers. So in this example, core is a conducting layer and it consists of strands, and the core screen is a semiconducting layer, and this is the main insulation XLPE, and then the insulation screen is again a semiconducting layer, and we have metal screen strands and also metal screen laminate. These are conducting layers, and the outer covering again an insulation. So this is a brief summary of the conversion methods. In the core conductor, it's of stranded nature, and we have to find out the effective resistivity if you know the nominal cross section and the material of the conductor. So this is the value you have to enter in PSCAD. So then there can be semiconducting layer between main insulation. Semiconductor layers are characteristic by high resistance and high relative permittivity. Typically, semiconductor layers are modeled as a part of insulation in EMTP models. The semiconductor layers change the effective permittivity value of the insulation. The effective permittivity value can be calculated from a formula, but in PSCAD you can directly enter the semiconducting layer information. All you have to enter is the thicknesses of the semiconductor layers. PSCAD will internally calculate the effective permittivity value. So the sheet can consist of wires. So this should be approximated by solid conductor with effective outer radius. And there can be dual layer sheet. Sheet consists of 2 layers, and this is again approximated by a solid conductor with effective resistivity. If you need more information about this, please contact us, or you can go to the PSCAD knowledge base. Another feature in transmission line and cable model is the mutual coupling between multiple towers. Suppose if somebody want to study the mutual coupling between different towers, there are two ways to model. So model all coupled transmission line in definition page of a transmission line, or using mutual coupling features. So in the first method, the towers are modeled inside the definition page of the transmission line, so that the mutual coupling is considered automatically. And these are the two towers 40 meters apart. So I change the relative expression of the tower center to 40. And another important thing is you have to correctly set the conductor numbers. So this is conductor 1, conductor 2, conductor 3, and you have to go to the base node connection information. Initially this is 1, 2, 3. You have to change it to 4, 5, 6, so that the PSCAD knows this the cable conductor number. This one is 4 and this is 5 and 6. Otherwise there will be an error. Suppose if you already modeled two transmission lines in different transmission line models, using the mutual coupling feature, you can combine them and study the coupling behavior. For that, you have to go to the edit parameters, and in the mutual coupling section, enable the coupling, and you have to define the unique couple segment name. For the other transmission line, so it is 40 meters away from the first transmission line. It's not the reference. There is one important thing. When you define the transmission line interface, you have to specify that these two interfaces are in one side of the transmission line, and these two interfaces should be in the other side of the transmission line. For that, what you have to do is you have to click this one and set segment and specification to sending. By default, it's automatic. You have to set it to sending. Similarly, for the line B, you have to send it to sending, so that these two work together in one side. And in the other side, this should be receiving, and the segment and specification for the other one should be receiving. Also in PSCAD, you can study the mutual coupling between overhead lines and cables. Overhead lines should be modeled as the area bare cables. So finally, I want to discuss about how to model a stranded conductor. For example, ACSR conductor. Here we have steel subconductors inside and the aluminum conductors. For modeling, forget about a steel part. Enter data for the aluminum conductor. So you have to specify total number of outer strands. In this case, there are 18 strands. Total number of strands is the total number of aluminum strands. There are 30 such strands. And also you have to define the strand radius and the outer radius of the entire conductor. Similarly, you can model the optical ground wires as well. So model them as a stranded conductor. Just neglect the optical part. So if you model the HVDC lines and cables, To obtain the accurate DC response, I have to enable the DC correction. I'm not going to go into much details. So this algorithm ensures accurate DC response. All you have to do is go to the phase model options, DC correction, and enable it. And you can select two methods, partial form or at fault method. You can use any method. So occasionally you may encounter the unstable simulation when you model underground cables. There are two things. One is caused by the large glaciers of residue faults in the transfer function. Again, I'm not going to go into much details. In later versions of PSCAD, set it to 2e⁻⁻⁶, very large value, so a new algorithm will be used. Another cause of unstable simulation is capacity violation. To improve the stability, in case if you experience such behavior, go to the phase model options, curve fitting, enable DC correction, and for underground cable you have to assign some adequate shunt conductors, and you can also reduce bound of fitting. These kind of actions you can improve the condition of passivity and the stability of the simulation. So there are a few questions. When you use long line corrected values, I think it's for load flow studies. You may need those values to analyze the transmission line. So that's where you need the long line corrected values. Those are the RSB values for the entire transmission line. The next question is, what happens if you get negative RSB values? All you have to do is forget about the long line corrected values. Calculate the total RSB values as the RSB values per unit length into the total length of the transmission line. So another question is that how do we know operating temperature of the cable? Well, there are some publications. If you go into CGRE working group C4502, usually 90 centigrade is used, but some publications suggest 70 centigrades. It depends. So in DC cable modeling, do we have difference with or without semiconducting layers? Yes, because it affects the capacitance of the cable. So semiconducting layers, if the data is given, you have to model it appropriately. So one question is, how to model the multi-core cable? I think talking about the pipe type cable module. Inside the pipe, you can define any number of cables, up to 8 cables. So you can model multiple cables inside the file. So one question is, how can I create a coupled phi section from a cable model? All you have to do is for cables or transmission line, the procedure is same. Go inside the transmission line and click on the canvas, select additional options. And then enable creation of equivalent phi section. Solve constants. So this will save a definition of the phi section to your temporary folder. Now you can go to definitions and import definitions. Here is my phi section, definition of the phi section, and you can import it to your definition and click on the definition and create instant. Anywhere in the canvas you can paste it. So this is my equivalent phi for this transmission line. You can follow the same procedure for the underground cable. Another question, is it possible to measure the voltage and currents on sheet conductors? Yes, you can do that. All you have to do is, if you have a sheet connection, you can measure the voltage of the sheet, current through the sheet. So these are the connection to the sheet. These are the connection to the conductor. You can connect any network to the sheet. But if you do cross bonding or conductor elimination, sheet is not available because it's a part of the earth. So when I have different lines with different time steps, which one should I use? You have to use the shortest transmission line and select the corresponding recommended time step. So that's the time step you have to use. So to model a DC line, all you have to do is create a transmission line, the number of conductors 2. In the master library there are inbuilt towers. This is how you create the DC line. One question, can we can many independent cables be modeled together, like has been done for overhead lines to get automatic coupling. Yes, you can do the same thing for the underground cables. So another question is, how can I simulate the cable underwater? I have already demonstrated. This is a submarine cable. So you have to change the resistivity to 1 ohm or 0.1 ohm based on the resistivity of the seawater, and you have to define the depth of the pipe, that cable. That's the depth below the water surface.
Okay, hello. My name is Lalin. There are a couple of questions on PSCAD cable applications, transmission line applications. One question is for TRV studies, which line model is recommended? If you're doing the station TRV studies, so the surrounding line can be anything. I mean, the important thing is the fault contribution through this line. So it can be either even the pi section is okay, because what you have to do is limit the fault current whatever the actual level. If you're studying station breakers, because the oscillation is more local, so there's no effect of the line unless otherwise it's a line breaker. If you are studying a line breaker, probably you want to do terminal faults or short lines or midline faults. So my recommendation is go with the phase model, because you need the traveling wave representation in short line faults. You need the correct damping. So in that point, you have to go with the detailed phase model. The other question is in the GPR calculation, ground potential rise in stations, how we should connect the sheath. You can go either way. I mean, you can individually grounded, or you can grounded with the substation system. The whole point is you have to maintain correct the grounding resistance. So as long as you put the correct grounding resistance, it doesn't matter whether you have individually grounded those cables or you just connected with the substation earthing system. So the importance is the correct the grounding resistance representation. There are few other questions too, so I think time is we have to stop now. So what we'll do, we go through all the other questions we couldn't answer today, and Jivant and myself, we will try to send you an email for everybody for these individual questions. The other thing is Kim will send you the link to the presentation and the cases, so you can download the cases and the presentation. So, or I mean, if you for some reason if you don't get answer for any of these questions, please send your questions to support@pscad.com. So our support team is happy to help you.
All right, everyone. Thank you very much for attending our webinar today. We look forward to seeing you again soon. Thank you.